complicated materials. And what you're going to see in the next 20 minutes are investigations using tunneling junctions of various aspects of the physics of transitions that metal dipole carbonide by superconductivity. I'm going to try to move this this bar of zoom that is in the middle of my field of view, and move my pointer to a laser pointer. Okay, so this work was done in my lab in Hebrew University by Tom Dvir, Itai Keren, David Astojet, Ayelet Salik, and Shachar Simon. I enjoy a very long-standing collaboration with the ORSA team of Marco, and Karis. I'm going to show data carried measured by David Lebuf in Grenoble, and theory was done by Maxime Chodas, Manuel Uzain, Julia Meir, and their respective students. And now let's see that this works. Good. So the outline of my talk, I'm going to talk about niobium, the sunlight, and tantalum sulfide as platforms for unconventional superconductivity. I'm going to show results from our experiments on layered superconducting spectroscopy. And at the end of my talk, I'm going to show how we carry out the same spectroscopy using barrier dots, barrier defects, which function as energy tunable quantum dots. So first of all, let's look at our experimental architecture. We start with a silicon substrate onto which we exfoliate a superconductor. It should be tantalum sulfide or niobium sunlight or anything else, which agrees with the fabrication philosophy, which could be down to a single monolayer if we want to, onto which we exfoliate the tunnel barrier. The tunnel barrier we use is usually another TMD, and the TMD we like using is moly-disulfide, but we basically, over the years, we have studied moly-disulfide, tungsten selenide, moly-selenide, tungsten sulfide, HB, and everything works pretty well with this method. And we add electrodes and we have our NIS tunnel barrier. And if we carry out the TM cross section, we see that TMD on TMD, this is the MOS2 barrier on top of the superconductor, engage very, very well. And I think my message here for the community is you really, really have to do this cross section before you interpret tunneling experiments, because many combinations of materials don't engage well. Iron-based materials don't engage well with the barriers. This is something we've shown, but the TMDs engage really well, so then you have an atomically defined tunnel junction, and you can be more comfortable that you're actually interpreting well-behaved tunnel junctions in your results. So now I'm going to talk, I assume that many people in the crowd already are well familiar with the TMDs. The main feature of the TMDs is the broken inversion symmetry. That means that there's a built-in electric field which points within the plane. This kind of built-in electric field cross-product with the momentum gives us an out-of-plane effective magnetic field which is independent, and that produces an effectively very, very strong out-of-plane spin-orbit term, which can reach hundreds of Teslas in its magnitude. And this is the basis for many of the phenomena that have been investigated over the past several years, mostly in transport by several experimental groups, noticing that these materials down to the monolayer are extremely stable to in-plane magnetic field. They can sustain superconductivity up to 30 Tesla and sometimes above. This is because the Cooper pair is stabilized by the spin orbit term with the electrons, the down and up spins at the K pockets, strongly pointing out of plane, and that means that if we apply an in-plane field, then we only tilt them slightly, but it's very, very hard to destroy superconductivity. Now, how is superconductivity destroyed by the in-plane field? This is actually subject of theoretical debate at the moment. So there's been several works by a number of groups by now. And my colleague Maxime Chodas has been very active in this field and with his former postdoc David Mokli. And they suggest a number of models, one of which is that if we look at the zero field pattern of the spins at the K points, the application of an out-of-plane, of the in-plane field tilts these spins, and the tilting of the spins introduces some kind of an equal spin triplet component. Now, that raises the question of what ultimately is going to destroy superconductivity, and here I don't think there is really a consensus, but it looks like there's the question of how will the various kinds of triplet components respond to disorder, where some triplets are more stable than others to disorder potential. And already there have been some works in the community showing that there are hints of triplet superconductivity by the group of Pribyag and also the group of Lords on thin niobium selenide at high in-plane magnetic field. So I'm going to move on and show our own results. And we have this structure of superconductor barrier. And This, for example, is a result on a 20 nanometer thick niobium diselenide. That's actually measured by Karis and Marco and Orsay at 17 millikelvin temperature. And we see a very well-behaved spectrum of niobium diselenide with the two gaps. There's a hard gap, meaning that there's at this logarithmic scale, there's a 3-order magnitude suppression of the subgap to over-the-gap conductance. And if we take the second derivative, we see very well-resolved two gaps, and that connects to the question asked in the previous talk, that yes, niobium diselenide is a two-gap superconductor, and this two-gap superconductivity is very well resolved in the tunneling experiment. Now, what we were able to do in this first generation of experiments was use in-plane magnetic field to be able to resolve the two different gap features. So if we apply an in-plane magnetic field below HC1, we have Meissner currents. Above HC1, we have lateral in-plane vortices. So below HC1, we depair the superconductivity by the Meissner current, and this kind of Doppler depairing can be seen at this second derivative versus in-plane magnetic field. That's HC1 of this 20 nanometer sample. That's the lower gap, which appears at about 600 microvolt. That's the upper gap at about 1.2 millivolt. And we see that the lower energy depairs faster than the higher energy gap. And if you look at the basic theory of depairing due to applied in-plane field, and you go to Tinkham, chapter 10, you can relate this kind of depairing to diffusion. And that means that if something depairs faster, it has faster diffusion, that means it has a greater Fermi energy. And we can indeed see in APRIS measurements that the selenium band, the selenium p band, p orbitals, have a 5 times greater Fermi velocity than the niobium d bands, which are here at the K and the bigger gamma pocket. And we suggest here that indeed our results agree with the second lower energy band superconductivity associated with the selenium p band. And that's also been suggested by earlier transport experiments in the 1990s. Now we can start turning the superconductor towards the thinner and thinner regimes. We start at 50, 25, 20, 11, 5 nanometers. What we see that this characteristic two-band superconductivity begins to disappear. And we notice that it disappears spectrally around 10 nanometers, which is about 15, 16 layers. At 5 nanometers, we no longer see any hint of two-band superconductivity. But now we can actually go as low as 1 or 2 layers, niobium diselenide, and that's an experiment we carried out in Grenoble. That's a 2-layer thick niobium diselenide sample, measured with an in-plane field up to 30 Tesla at 1.2 Kelvin. And what we can see here is that the gap, of course, is no longer hard because of the finite temperature, but it starts filling up. And although the gap starts filling up at these very high in-plane field, we see that the size, the magnitude of the gap feature remains more or less stable. Now, that's really not trivial. And it's not entirely clear what would stabilize the gap. And we've been working for almost 2 years on the analysis using with the help of the various theory groups. But what we see here is that one has to invoke something just beyond the simple picture of a single band, even if you have IZ protection. And one model developed by Maxime and by Julia and Manuel was invoking another order parameter, which is a triplet order parameter. And one can see, invoking this model, that if you look at this data set, this is our data set, and you extract delta indeed becomes stable, and you can see that the theory fits data slightly better. I must add that right now we're also working on another model which invokes the role of the gamma niobium carriers, and also there might be some contribution to this kind of excess stability. So I don't think we can make a clear. I don't think we can close this question right now, at least based on theory, but I think it shows that there's a relatively rich complex effects which kick in at the spectra of this material at very high intensity. So I'm going to now move on to some results on tantalum sulfide. So I've shown you the full spectra on niobium diselenide with the quasi-particle peak at about 1.3 millirad per volt. If we go to tantalum sulfide, the gap becomes way smaller. That's bulk tantalum sulfide. That's measured in 20 millikelvin in our dilution class. The gap is 180 microelectron volt. With tantalum sulfide, there's a very interesting effect that the gap starts increasing in its magnitude as the material grows slower. That's the biggest gap material that we measured, which is presumably one layer tantalum sulfide. And we can make a number of statements by now when we measured a relatively large number of samples. These are all results by my student Shachar Simon. We can see that the critical temperature increases, and that more or less follows results by groups who've been studying this using transport, Ben Hunt and Pablo Herrero. And in addition, we can correlate delta to TC, and we can see that delta and TC align very nicely according to BCS theory with a slope of 1.76. And finally, we can also compare the HC2, which we evaluate by the magnetic field where the spectral features attain a spectral density, the normal state density of state. And we see that if we start with very, very low HC2 of less than 1/10 of a Tesla, in the bulk tantalum sulfide, this value goes above 1 Tesla for the ultra-thin tantalum sulfide. And here, if we compare HC2 to delta square, where clean superconductivity is expected to give you a certain results based simply on the relation of the coherence length to delta, and that implies that you would expect some kind of proportionality relation, and this proportionality relation holds more or less up to these samples, which are about 4-layer samples. Once you start moving to 2- and 1-layer samples, HC2 diverges. Now, these are new results. We haven't carried out a thorough theoretical analysis, but I think it points to something rather unusual happening to the superconductor at this regime. Perhaps another band kicks in, perhaps something changes to the kinematics, of maybe there is a maybe enhanced or suppressed Fermi velocity. I don't think we can tell, but we can tell that there is phenomenologically something that's unusual that takes place. So now, since I have a few more minutes, I'm going to show recent results where we use tunneling spectroscopy, but not using tunnel junctions, but rather using a defect state in the barrier. This is the experimental geometry. We have 2H niobium diselenide of finite thickness. The barrier is MOS2. The barrier has defects, and you'll see in a moment how we know they have defects. The tunneling electrode is graphene, and graphene resides on top of silicon oxide and is bottom gateable. And if I look at the IDV spectrum, I see a well-behaved niobium diselenide, the IDV spectrum. We've seen a few of those in the past few talks. But what you see here on the right side, I have to move my zoom. It is hidden behind my zoom window, so I cannot move my cursor there. But if I measure the IDV spectrum at different gate voltages, the spectrum changes. This means that something is gate tunable, and I'm going to show in a moment that what is gate tunable is the energy of the defect. Now, this is the total signature, VSD versus backgate, and you see that there's this is the niobium selenide gap, and you see these diagonal features over here. And these diagonal features are just a single replica of a Coulomb diamond, and if I subtract a constant background, I see very well these slopes of the truncated Coulomb diamond with a gap that appears here. So I'm going to focus on this gap and see what kind of spectral information I can extract from this gap. And I haven't shown here, but the reason that I can tune the energy of the dot is that graphene permits, the graphene tunneling source electrode permits finite electric field to reach the defect. This means that the defect is gate tunable and is also energy tunable. This is just a fully tunable quantum dot. So if I can tune the energy of the quantum dot versus the superconductor, then I can basically find a trajectory on this VSD versus gate plot where the defect energy is coupled to the source energy. These are these trajectories that I'm marking now here with my cursor. They're marked here. And this means that in this blue trajectory, which is kind of a reference trajectory, the dot is Coulomb located. So I'm not going to see any dot-assisted tunneling. But in this trajectory, where the dot is not Coulomb located, that means that I have dot-assisted tunneling. So I'm slicing various parts of the spectra as I move along this trajectory. This is exactly what we did, measuring along this diagonal trajectory. This is the diagonal trajectory where we use the dot as the spectrometer. So if we take the measurement, we see 2 peaks here. There's a spectral feature at 600 microvolts. Yeah? What do you say?
Yeah. 2 minutes.
2 minutes. Fine. Good. Very good. 600 microvolts, 1.2 millivolts, and these are the same two gaps of niobium diselenide. This is the lower energy gap, this is the higher energy gap. You've seen them before. Now, fortunately, in the kind of device that we have here, we have direct tunneling from graphene to the superconductor, where the second derivative reproduces the same peaks I had before, the lower energy and higher energy features, and dot-assisted tunneling, where I still see the same two peaks, but at different intensities. So having carried out the full analysis, and the analysis using the Macmillan model, which reproduces two-band superconductivity in niobium diselenide, we can argue that we identify the same two bands, but the only difference between the tunneling spectrum is the selectivity of tunneling directly or through the dot into the two different bands of niobium diselenide. And as I said before, the lower energy band is selenium related, and we suggest that the dot-assisted tunneling is actually dominated by these selenium carriers as respect to the direct tunneling, which extended state tunneling, which is dominated by the niobium carriers. And I'm going to finish my talk by noting that there are, since we have only single quantum dot data reported in this paper by my postdoc David Estajet, that appears very recently in Nano Letters, we can argue that there are a number of possibilities. One is that we have the dot residing at closer proximity to selenium rather than to niobium at the XY plane. Another possibility is that there's a momentum selectivity where you see that the selenium resides much closer to the gamma point, and in momentum space, since the dot is a constant point, there may be favoring of these lower momentum states, and there could be also orbital selection rules related to the kind of defect which is active in this particular device. I'm going to skip this because I'm out of time. So in summary, we use stack devices as platforms for high resolution spectroscopy, and we can use defects as quantum dot spectrometers, and these defects have various selection rules which perhaps could be useful in designs for future systems. Thank you very much, and then I hope I'm in time. I think superconductivity is going to dominate the pairing at the very, very thin limit, because that's where you suppress the orbit, you suppress the orbital contribution. And I'm going to flash this one slide over here that shows that we can actually see this kind of depairing effect only above a certain thickness. And so above, you can see here by 5 nanometers, you hardly have any response of the system to the magnetic field, because you fully suppress the orbital component. At 25, 50 nanometers, you have a very dominant orbital component, and this orbital component is going to depair, albeit at different rates, the carriers of the niobium and the selenium carriers. The Ising kicks in only at a very, very thin limit once you have suppressed all other sources of depairing in the system. And you have to be somewhere below a few nanometers, the few layers for this to be observable. So everything I've been showing about this differentiation of selenium and niobium, that's a finite thickness of the sample.
Thank you.